Hello and greetings, everyone. This is Volts for March 25th, 2026. For data centers, a little flexibility goes a long way. I'm your host, David Roberts. By now, most Volts listeners are familiar with the crisis facing the electricity sector. After decades of plateau, demand is rising again, quickly. Giant data centers are banging on the door, demanding to be hooked up to the grid. Interconnection queues are clogged, and some grids, like PJM's, are basically maxed out. Everyone, utilities, PUCs, legislators, and the public, is scrambling to figure out how this should work, how the system can grow to accommodate the AI boom without placing all the costs and risks on ratepayers. One solution that is gaining considerable attention is flexibility in data centers. Conventional energy models, including those used by utilities to project demand, assume data centers are always on, always consuming at their rated level, which in the case of some of these new data centers is as much as a gigawatt. Guaranteeing a gigawatt of steady service 100% of the year, come what may, is no small thing. That is one reason utilities have been slow to connect these things. But what if they didn't have to guarantee 100% of service 100% of the time? What if, say, 10 to 20% of the time, data centers could survive on their own, running on their own batteries and backup generators? That little bit of flexibility could enable utilities to avoid tens of millions of dollars in grid upgrades and connect many more data centers much faster. At least that is the argument in a new study and white paper on the subject. It is a team-up among the energy analysts at the Princeton Zero Lab, the energy modelers at Encord, and the flexibility software startup Camus. A couple of those names probably sound familiar to you. Indeed, today's guests have been on Volts before and are some of my all-time favorite guests and people. I have with me today Astrid Atkinson, the CEO of Camus, and Jesse Jenkins, the head of Princeton's Zero Lab. We are going to discuss what exactly this model looks like for data center flexibility and what sorts of benefits it promises. With no further ado, Astrid Atkinson, Jesse Jenkins, welcome back to Volts. Thank you so much for coming.
Thanks, Dave.
Yeah, thank you.
There's a lot to talk about here, a lot going on, so much going on in this space. But I want to start, before we get to what they ought to be doing, what data center developers ought to be doing, let's talk briefly about what they are doing. My impression, and tell me if this is wrong, my impression is basically that everybody involved is in a big old sprint for gas. Like, to me, I look out there, I see data centers scrambling for off-grid gas capacity. I see utilities scrambling to build gas capacity. I see gas companies gearing up for historic demand, no end in sight. Like, this whole thing looks like a gas disaster to me. Is that wrong? Jesse, maybe you start. Like, it looks to me like the only way these guys can figure out how to get data centers online at the moment is by surrounding them with a bunch of freaking like jet engines, basically.
Yeah.
That seems crazy to me. Is that in fact crazy?
I would say that's definitely where the zeitgeist is at right now. There's the sort of default assumption is that, you're just going to build a bunch of gas power, whether it's a combined cycle plant or a simple cycle open, cycle gas turbine like that, the jet engine you mentioned, or even reciprocating internal combustion engines, like, basically big diesel gen sets that can run on natural gas. Halcyon is tracking 85 gigawatts of gas plant additions currently planned across the US. And it is quite a potpourri of different designs. And I guess, some of those are grid connected. Some of those are utilities, sort of happy to say, yep, I'll build you, 2 gigawatts of new gas generation if you connect to my transmission grid. But a good chunk of those, and a very rapidly growing piece this year, is behind the meter projects. So projects where they're actually just trying to build these generators on site. I think maybe one emblematic of that is the XAI training center outside of Memphis, the so-called Colossus facility outside of Memphis, Tennessee. It's kind of right over the border in Mississippi, parts of it anyway. They basically rolled up with over a dozen gas turbines on trucks, like on the back of a flatbed, and plugged those in and have been running, these sort of intended to be temporary generators pretty much nonstop. They initially tried to sidestep air pollution rules, saying that they were not applicable because they were mobile generators. The EPA has since said, no, actually, we thought about this before, those count. But the Trump administration's EPA is not actually enforcing any rules. So they are basically violating the rules, but with no enforcement, to rein them in. And now they're asking to build over 20 permanent gas generators on site, to which the public resoundingly said no recently at a kind of February open meeting in Mississippi. So these are, that's, I think, emblematic. They were sort of the first ones to get to a kind of gigawatt collective scale training capacity, and, been touting that. And they did that basically by, building their own, small, meant to be temporary gas generators and just running them continuously in order to avoid having to wait for projects to come online on the grid and supply their energy. And I think once folks saw that, and then other projects have been announced, that model has started to spread, and it seems to be kind of the default stance of many developers right now is, the grid process is broken, so, forget it. I'm going to go around it and build my own generation on site. And even if that's not an efficient combined cycle power plant, which is what you would want to do if you were using gas, well, it doesn't matter. You're like, they'll pay for it.
Before we move on, I just want to talk about, aside from, I guess we all decided not to talk about climate change anymore. So, maybe I'll just mention, seems real bad on the climate dimension. There's a lot of emissions, but I just want to ask about operationally. Like, it's crazy, right? Like, this is not how you would run a data center if you were setting out to run data centers in a rational way. Like, it's crazy. These turbines they're using are not meant to do what they're doing. Am I wrong about that?
Yeah, I can maybe offer a little bit of perspective on this because part of my past life was in the reliability organization at Google, which deals a lot with the intersection between software and physical infrastructure. So a little bit of experience with working with data center infrastructure. And I think firstly, like there is a real risk of locking in a lot of gas generation to meet this demand growth need. Having said that, on-site, fully off-grid natural gas generation is not great from a data center perspective. Like to your point, the reliability profile is not great. You need a lot of redundancy to be able to do this on-site. Personally, like I would be concerned about things like vulnerability to natural gas price fluctuations, as well as deliverability challenges.
The more I think about this, the crazier it seems. Like if one of these big gas generators that's off-grid goes out, like these data centers want 5.9 reliability or whatever it is. So if one of these generators goes out, you have to have then on-site
a backup
generation sufficient to cover that. So you are building like double the capacity you need in natural gas on-site. That seems crazy.
Yeah, and they're also, apart from anything else, they're not quick to build. So it's not clear to me that this is actually a really fast path to power solution in the way that folks on the tech side are maybe hoping that it is.
Yep.
And also, in practice, what we are seeing is that while there's a lot of discussion of fully off-grid sites, what I've heard from utilities working with a lot of these sites is that what the utilities will say is there's no such thing as a fully off-grid data center. That in practice, there's still a lot of crosstalk and kind of cross-traffic looking at opportunities for grid connection. So I think there may be a little bit of a gap between exactly what people are hoping for and exactly what's happening on the ground.
Yeah.
Yeah, I mean, I think it's just funny how this sort of the zeitgeist shifts because, like, if you were talking to somebody in 2024 about whether data centers would go, entirely off grid, the answer was absolutely not. Data centers need 5 nines reliability, and so they have to have grid connection.
It's crazy for obvious reasons.
Yeah. And so now, the reality of actually trying to connect to our grid and all the fragmented and broken processes that entails, and that has started to sink in. And so everybody's sort of searching around for an easy button solution with increasing levels of desperation, I might add, like, going out and trying to refurbish old jet engines from decommissioned aircraft and like get them back into service, or use marine diesel engines, things like this. So I look at this and I just see like this is broken, right? This is a sign of the fact that we are kind of between a rock and a hard place. The rock is the growing demand, which is very real, for 100 plus gigawatts of peak demand growth by 2030, most likely. And the hard place is that our grid and its institutions have not been designed to keep up with both general load growth, but also the scale of these facilities. I always like to stress for folks that a gigawatt is that's bigger than the entire Pittsburgh metro area or something like that. It's like plopping down an entire city.
These are like small cities.
Yeah, not even small cities. I mean, a gigawatt is a big city. So, you're trying to connect a city's worth of demand in one location on the grid. And that's just not a trivial thing to do, even if our institutions were working well, which they're not. So it is, I think, a sign of increasing desperation. And I don't think many of those behind the meter or largely behind the meter projects will actually pan out as intended. And so, the question is, what else could we be doing better than this? Because this seems kind of nuts.
My worry is that while we're trying to figure out a better way, we're just locking in a lot of this gas. Like, these are going to be stranded assets. Like, you're going to own all these turbines and jet engines and everything. They're going to want to use them. I just worry that we're like digging.
I do think that's a risk, because there's a couple of factors going on here. One is that it's likely that while there is a lot of real demand out there, that the current queues and any individual project has some risk associated with it, because not all of them will end up being built. And that means that we'll likely build generation in places to support sites that don't end up happening.
Yeah.
And then we do have a lock-in problem. The other thing is that there's an alternative path which could support a lot more development of grid-connected generation, whether that's fossil or renewable. It gives us a path towards, over time, further decarbonizing our overall energy mix on the grid. I don't want us to miss that opportunity. So I really see this as a fork in the road.
It does seem like a fork in the road, and it seems like, I was talking with Jesse about this off mic before, but like, this is the rare problem. Like, most of the problems people in our world have encountered are regarding incumbents who feel no particular need to change, and we're just outside, beating on the doors, yelling at them. But here we have like, everybody recognizes that this is broken. Everybody recognizes that this needs to happen, and they've got lots of money to spend on solutions. So this is like a problem space where things are actually happening and everyone wants to solve it, which is not typically the kind of problem we deal with. So Astrid, then let's talk about this model that you are proposing here in this paper. There are two basic parts of it that I want to sort of take in turn. There's the flexible connection part, and then there's the sort of power park part. There's the bring your own generation part.
Yep.
Those are the two parts of this model that you're proposing. Let's talk about the flexible connection first, because I sort of alluded to that in my intro. So describe the typical connection and then how a flexible connection would be different.
Yeah, so the typical connection for data centers, which has been the industry practice up until the start of last year, and in practice is still the only way data centers are really getting built today, is to have an interconnection that supplies you with 100% of your peak power need. It gets you nameplate capacity from the grid. So, we've talked about there being potentially a lot of interest in bringing on-site generation or battery. That is not really, firstly, something that is accounted for in that traditional interconnection mechanism. We've also further talked about the fact that there might be a lot of additional capacity available if you're able to be flexible around the few hours or, even up to maybe a day or two of the year where the existing grid is otherwise at peak and is full. If you can avoid those peaks, there is an additional amount of current grid capacity that we can unlock. And so there's kind of those two ideas of what we're talking about when we talk about flexibility here. Broadly, what we're saying is that if we could update our interconnection model to allow a site to sometimes use less than their peak capacity by agreement with the grid operator, whether that's by going to flexibility or going to local generation or whatever, that we would perhaps be able to interconnect that site more quickly with less transmission system infrastructure required, and potentially also with less overall generation capacity required to support that like kind of stacked peak demand.
Right. And this is, as far as I know, something that only ERCOT is doing currently, i.e., they'll say, sure, you can hook up with the proviso that a few hours a year, we're going to cut you off. And it turns out that just that few hours a year unlocks a boatload of more capacity. So I guess, is ERCOT's current practice what you are talking about? And basically is what you're asking for just other utilities to adopt that same model?
It's close. So a couple of things. Firstly, ERCOT has a connect and manage model for generation. And that's really what we're looking at here for load, right? It's basically saying...
They don't have it for load, though, there in ERCOT, at least
not yet.
Interesting.
It's in progress. So they do have a rule that enables loads to be curtailed as part of the overall security-constrained economic dispatch. What they're working on is a corresponding set of rules that enables that capability to be taken into account at interconnection time. So it's a work in progress there, but that's basically the goal.
Yeah, it's worth breaking out. There's really kind of two obstacles that have to be overcome in order to get a data center online, right? One is you have to have sufficient transmission capacity to connect. And that's, your local substation, but more importantly, it's also, deeper constraints that may be caused throughout the grid when you add a city's worth of demand at some point, and then that reconfigures, power flows in pretty important ways. So that's a very localized thing. And generally, the approach to accommodating new loads has been, let's run the study and make sure that we upgrade the grid so that that load can always be served and that those constraints are never binding effectively on the load side. And that is not that's a local transmission owner driven process on the demand side right now, as opposed to a FERC, federal jurisdictional entity like the regional transmission organizations, which do interconnection for generators. Now, there is a proposal to shift that potentially to the federal level that FERC is considering, but right now that's done differently in every transmission owner jurisdiction around the country. But the general rule is, make sure that there's no issues, no constraints that are going to bind our ability to serve this load.
Which is just like an incredibly conservative, defensive, very conservative way of doing things.
It is, and it's sort of consistent with this idea of that the utilities all have an obligation to serve and that everybody deserves a sort of reliability. So that's the traditional thinking, but these are not traditional players, right? It makes sense not to treat a giant data center the same way that you would treat my EV charger or a commercial office park, right? They're not the same thing. And so that's the first constraint. And then the second constraint is that you have enough generation adequacy or, accredited capacity so that you can actually supply the data center with power when it needs it. And again, we traditionally rely on the grid for all of that, right? You have to go to the market and get a supplier to meet your needs. And those suppliers have to show that if you have 100 megawatts of peak demand, that they can deliver 100 megawatts of accredited capacity or, energy available whenever you need it. And again, you could get some of that from the grid, and some of that you could be supplied by your own ability to curtail your demands from the grid. And so these two barriers, the transmission constraint and the generation adequacy or capacity constraint, are the two things that every data center kind of has to overcome if it wants to connect to the grid. And we need processes that recognize that there are other solutions besides just wait for the utility to solve the whole problem or do it entirely off grid behind the meter with your own gas plant.
Right. So the two parts, as I said, this is a two-part plan. The two parts are to address those two constraints. So the flexible interconnection thing that we're talking about now, that's to address the transmission constraint, basically. If you're transmission constrained, this basically makes more use of existing infrastructure.
Yeah, and the flexibility side can also help to adjust the generation constraint as well. Because as Jesse mentioned, that could be either the data center curtailing its own usage, could be the data center switching to battery, could even be the data center procuring accredited capacity from a VPP. But there's a few different ways that flexibility can support on the generation side as well as transmission.
So when we talk about then the generation side, client side, generation, resources that can cover for when the grid is not supplying power, what are we talking about? I mean, as we said at the beginning, mostly we're talking about gas, at least the ones that are going up right now, they're talking about gas. What do you envision? Like, what is the solution space there? What kinds of things could they bring?
Yeah, this is where we get to our fork in the road. Because a lot of the conversation today is centering around gas. But there are alternative models that are live in the market today that look at basically what you referred to earlier as the power park approach, where you will potentially have a portfolio of resources supporting the data center. And that could be solar and storage that's nearby or on site. That could be renewable development under PPA that's further away but is accessible via transmission connection to the site. That could be flexibility resources, other than generation on site. So
batteries mostly, right?
Battery load reduction, all of the above.
But mostly batteries, right?
Yeah.
Maybe solar. It depends on how much base you have.
Could be. But collectively, looking at the power challenge as a portfolio approach that uses, some grid power and some new generation, which ideally is renewable, along with a lot of battery, is the alternative to natural gas. And we did look at this in the paper too. And I know Jesse will probably have some perspective on this kind of portfolio approach, but what we did when we put the paper together was for each of the sites, we modeled the flexibility requirement that would be necessary to get it connected to the grid at its target capacity.
Right.
So how often would you have to be flexible, by how much, these things.
Right.
And then what we did was model basically what would be the stack of resources that would serve that additional need. Like, where would that flexibility come from?
Mm-hmm. Where did it come from?
Well,
do tell.
So for some of the sites, battery alone, as well as some component of on-site load reduction, was enough. That was true at, I think, 3 or 4 sites. At a couple of the sites, there is potentially a role for natural gas as a firming resource. And, that's obviously up to the developer as to the choices that they want to make about their power mix. We also, at the request of other participants in the study, modeled what it would cost to not do that. To say, like, look, what if we just wanted to build a lot of battery instead of that natural gas plant? And it costs, another $1 billion or $2 billion.
More to do batteries than to do natural gas.
A little bit. But the data centers are really expensive, and it still comes out net positive if you connect more quickly. So there's a lot of room for improvement here.
I see. And do we think, batteries are going to get cheaper, too? I mean, they're getting cheaper and cheaper.
Yeah. They are, and that's helpful. And at the moment, gas turbines are getting more expensive, and gas prices are going up. So that does help close that gap a little bit. But I wanted to highlight something. As we talk about batteries, like we typically think about shorter duration, 4 or 6 hour kind of dispatch.
Yeah, long duration plays a role here.
Well, it might. So, but I wanted to actually go back to something you said in your intro, which is like, well, what if data centers could be flexible 10 or 20% of the time? That would unlock a lot. It's actually less than 1% of the time.
Yeah.
Yeah. Well, you're jumping ahead, Jesse. You're jumping ahead.
Well, but this is important, I think, to understand the role that batteries can play in relieving these constraints. Because when we looked at the constraints, so Encord, which is one of the 3 organizations that did this, did actual optimal power flow modeling for a real transmission system that was, provided and vetted by a utility, looking at 6 different sites across that system where you could potentially host a 500 megawatt data center nameplate, capacity. And what they found was that in 2 of those sites, there were basically no constraints. And in 3 of the sites, the annual curtailment in total was 7 hours, 11 hours, 13 hours, and 35 hours. So that's like at the highest end, 0.4% of the hours of the year. And the longest events at 3 of the 4 were 5 hours long. And in the 4th one was 16 hours. And there were only 3 or 4 of these a year. So these are, with the exception of that 16-hour event, those are perfect for batteries, right? They're the right duration for a battery to be able to ride through the entire length of the event.
Let me just clarify this for listeners. So that you did the model, the premise of the model is that these data centers are making deals with the utilities saying, you provide 80% uptime, 20% we'll cover ourselves. But that's on paper, but in practice.
No, the concept is actually, you connect us, and you don't charge us for any transmission upgrades, because instead of making those long, those costly and more importantly, very slow transmission upgrades, you can dispatch us instead to reduce our consumption at the point of interconnection to avoid any of those constraints. So it's an operational strategy that in lieu of a wires upgrade.
Right. But the contract says up to 20% of the time. But in practice, when you run the model, they're actually only called on, they're actually only curtailed. It's not even close to 20% of the time. It's not even close to 10% of the time.
Yeah, I don't think we constrained it.
But the model that we used was one where there's basically a firm capacity allocation and then a flexible capacity allocation.
Yep.
So the firm capacity allocation gets served like normal load. You get it 100% of the time, it's guaranteed. The flexible capacity allocation is a margin on top of that that's available some of the time. The reason that we split it that way was that allows the data center side to bound the problem. They can say, look, I have 100% of this much, and then this other capacity is contingent on being available from in terms of grid capacity. And on the occasion when it's not, I will fill in the gap on that. Then there are some further constraints around that, ideally within an interconnection agreement, to say like how, what kinds of contingency events or what kinds of flexibility events might be called. So that's where, you get the like maybe up to 20% of the time for the flexible allocation only. But there's a couple of dimensions in here that increase the reliability on both sides of the conversation, and that's important.
But I think the thrust here is that just a few hours of flexibility a year. We're not talking about a ton of time here. Like, it's only a few hours a year in practice where you need to bring this flexibility to bear. And those few hours get you so much.
Yeah.
Yeah, it's only a few hours, and it's only a few hours long each time it occurs is the other key, piece that for at most of these sites. And look, there's variability. This is going to be different at every point in the grid, which is why you still are going to have an interconnection study, right? You're going to have to say, all right, where can I connect where there's headroom? And traditionally, what data centers developers have done is go around looking for places where this isn't a problem, where there is headroom, right? Where you can sneak on the grid and connect under its existing capacity without causing any upgrades besides the substation you need to connect. The problem is those sites are not available anymore, and the scale of data centers are not, like a 50 megawatt data center 5 years ago was a big data center. Now we're talking about like 500 megawatts, 1,000 megawatts. Like, yeah, there's no gigawatt of headroom lying around in most places. So what we're basically saying is there are maybe locations where, yeah, if you tried to connect there, you would have to curtail 50% of the time, but maybe just don't connect there, right? Like, there are other locations. And in this case, we found 6 of them within this one utilities territory, right? And there's probably plenty more, where with just a few hours of flexibility, you could bypass those kinds of transmission upgrades. And once you do that, now you have access to the broader grid and all of the energy and capacity that it could deliver, from all the various options that can flow through that grid, as opposed to just what you can build on site. And that's the other big unlock here.
Yeah.
Sure. I mean, you want the grid as backup.
There's a reason we have a grid, right? We started with little microgrids with every factory having its own diesel generator, right? Or its own coal-fired reciprocating engine.
It's quite effective. It works quite well.
But the grid is much better.
Yeah, and this is where the inefficiencies that are kind of baked into current grid planning become really interesting, because the way that we design the grid today is with a significant amount of contingency capacity for being able to continue to serve either during peak time or during outages. And that contingency capacity is rarely used. It's really only called into play during an outage. But because of that, we have pretty low overall utilization of our grid as a whole.
Yes.
Yeah.
This is a subject we're going to be talking about here on Volts quite a bit in coming weeks. So just say a little bit about what your study, because you did a study of this.
Yeah. So as part of the study that we did looking at these data center sites and the role that flexibility can play, what we were really looking at is basically like, what is the unlock for being able to be flexible some of the time? How much additional capacity could we get? Our back of the envelope calculation is that it's somewhat on the order of about 30% once you take into account regional variation and the practical considerations of, how much flexibility could you really bring and what does this look like from region to region? So that's just kind of a guess. And Jesse's Princeton team did some of the modeling around this. But the other thing that's worth considering here is that the grid is somewhat over-provisioned for everyday usage.
Right.
This is not the first time we face the challenge of needing infrastructure to do a lot more work. This idea of oversubscribing physical infrastructure, basically like scheduling a bit more work than it could do at peak, is the foundation of how our other networks work. Like that's how the internet works. It's how our telecom
Can
networks
you unpack
work.
that a little bit, that notion of oversubscribing? I don't know that my head is totally wrapped around it.
Yeah, absolutely. So the way that we capacity plan for the grid today, we're looking basically at a strict worst case scenario, right?
Right. What's the peakiest peak?
That's right. At the peakiest peak, how much capacity do we need to serve all of our demand?
And assuming that a few things fail at that moment, right? You know,
Totally.
a big transmission line goes out or a nuclear plant goes offline, these contingencies that they also layer on top of that peak.
Yep.
That make it even harder. Yeah.
Which means that in practice, a lot of resources are sitting idle a lot of the time.
Yes.
And this is something that, we've faced in other contexts as well. So I think a really interesting example on this is actually from within the data center space. So I used to work in reliability at Google, and a lot of that was around thinking about systems and network and application infrastructure that would allow us to operate systems reliably. But about 50% or more of the work involved was actually looking at resource efficiency. How do you get more usage out of your really expensive capital assets that you can't get more of in a hurry, your data centers?
It's all about flattening peaks. I mean, in whatever
is.
context, right?
That's right.
It's about flattening those peaks.
So a lot of what we worked on in that context was basically like, okay, well, we've provisioned N+2 capacity for data center resources, right? Like, let's say that you're serving web search. You've got maybe 10 web search clusters in different locations. That's how many you need to serve web search at its peakiest peak. Then you've got another 2 clusters in other data center locations in case you lose 1 or 2. So now you've over provisioned. You've got an N+2 capacity situation, which means that you have a lot of very expensive compute resources sitting idle a lot of the time.
Yes.
And so the idea of oversubscription is basically the idea that you could say, like, look, sometimes I need these resources, occasionally, but the rest of the time they're sitting around idle, and that's really expensive for us, and it's limiting our ability to do work. So how can we get extra work out of those resources opportunistically? And so the idea of oversubscription basically says we'll schedule a bit more work onto those resources than they can do at the peakiest peak. And we can do that because we have tools to remove some of that work at the times when the capacity is needed for its primary purpose. So that's something that sometimes happens within data centers. Not all data centers are operated that way. It's definitely something that happens within how we operate the internet. Like the internet has a notion of like quality of service tiers, where when it's extra busy, it'll drop the lower tiers in favor of only serving the important ones. And it's also how things like 5G and cellular networks work. They're heavily oversubscribed. They have tens, maybe hundreds of times more traffic signed up to use them than the network can actually sustain. And they just kind of cleverly drop load at certain times to make that possible.
Yeah, you don't necessarily notice, but you're getting throttled back in terms of your bandwidth all the time.
That's right.
Interesting. A couple of questions about this, about BYing your own seat. BY, you guys didn't go for the Beyonce, sadly, I guess, because you're trying to make room for gas to bring your own new clean capacity.
Clean energy, yes.
I think it was just a failure of imagination.
Yeah.
Well, we use Beyonce around here at Volts. But
I love
this
it.
model, a couple of questions about it. One is, if you add to the complexity and cost of building a data center the additional complexity and cost of building a power park next to it, are you skewing the market in favor of big players, basically? Like, are you at risk of sort of wiping out kind of the guys in the pickup truck in the lower end of the market? And should we care about that? Hey there, everybody. Don't worry, I'm not going to tell you about a new mattress or push a credit card on you. This isn't an ad. There are no ads on Volts. It is supported entirely by listeners like you. If you'll indulge me for a second, I'd like to ask for your support. I started Volts because we're all surrounded by depressing news about climate change and misinformation about clean energy, and it's never been more important to share the stories of the real people on the ground doing the real work of transition, and all the ingenuity and courage and public spirit they are bringing to it. People are hungry to hear these stories, to learn from and find inspiration in them. I've heard from people who changed majors or careers after hearing episodes of Volts, people using it in classrooms and community groups, even state legislators who have passed bills inspired by specific episodes. Sharing these stories matters. It makes a difference. If you have found value in it, and want to help me continue doing it, I hope you will join the community of paid subscribers at volts.wtf. It's about the cost of a cup of coffee a month. If you don't like subscriptions, you can make a one-time contribution, leave a review on Apple or Spotify, or just tell a friend about Volts. I am grateful for any and all support. If you're already a paid subscriber, thank you. And now, back to the show. Are you skewing the market in favor of big players, basically? Like, are you at risk of sort of wiping out kind of the guys in the pickup truck in the lower end of the market? And should we care about that?
There's not a lot of really low end of the data center market.
Yeah, not anymore.
Everybody's big now, I guess.
Everybody's pretty big.
Yeah, and I would say that in terms of bringing your own capacity, I mean, the idea is once you've solved the local transmission constraints with, some amount of flexible interconnection, which is backed by either compute flexibility at the data center itself and or typically some combination of compute flexibility and on-site generation or storage, then you basically have the ability to get around transmission constraints when they're relevant. And the other 99% of hours of the year, you have access to the whole grid, right? I mean, you can't go from Kansas to New Jersey potentially, but you have a much wider catchment that you can draw on. So you don't need to build a co-located power park right next to your data center. That is an option. It's really only an option in certain places like West Texas or Oklahoma where you can actually build a gigawatt's worth of supply in one location. That's what, Intersect Power, which is just acquired, their pipeline was just acquired by Google, is doing at a few locations. But what my company, Firma Power, that I started recently, is trying to do is say, well, once you've got that unlock, where are the wind, solar, storage, demand flexibility, VPP resources across the much broader grid that if you assembled them in the right optimized portfolio, could deliver all 100% of the accredited capacity, meaning it can get you all the energy you need when you need it, and some fraction as desired by the customer of the energy on an hourly basis that they need as well, and deliver that to the site of the data center using that old-fashioned grid that we've built, for a reason.
So you're assembling like a virtual power park, basically.
Yeah, I guess you could call it that, but it's just the grid. This is just how we do power, right?
But this is what you're calling nearby but not on site. And I think both those are important. They're not on site, so you don't have to build everything behind the meter, but you do need, if you're going to buy capacity resources that are not on site, you do need them to be on the same grid.
Yeah, I mean, there are differing constraints that utilities apply. So they're basically, you can't be, there's sort of what we call the kind of big C capacity, which is the accredited, the formally accredited capacity as designated by PJM or MISO or SPP or whatever the capacity market entity is in the region that you're in. And they each have different formal constraints about, how far you can move capacity from one region to another. You can't necessarily go from one side of their market to the far other side, but you generally can move it at least, adjacent, to adjacent zones across a fairly wide area. But then there's also the little C capacity, like what actually is deliverable during operations and what will the utility that has to agree to connect this resource actually trust to show up when they need it. Right. And so, the basic picture is, we have to widen our view out from just the constraints caused locally by the data center connection and think, are there important binding transmission constraints between where this, wind farm is or this large battery project is and where the data center is? And if there are, do those occur at times when we don't have available resources on the other side of the constraint, right? When it actually is one of those binding capacity periods. And that's exactly what our company's trying to do is, that's not a trivial thing to say definitively. It's not trivial to identify the right mix of wind, solar, and battery resources that kind of operate collectively to meet your needs. Their capacity accreditation evolves over time because as the mix of resources in the grid changes and as the demand changes from electrification or data centers, the times when the grid is stressed moves around. And so solar might be great in the summer afternoon, but it's not good at night in the winter. So the values of these resources change over time. And so what we're trying to do is basically design optimal portfolios that manage all of those risks for the customer and take care of that complexity. And if we can do that, then we can unlock hundreds of gigawatts of resources in the queue already under active development, ready for deployment in 2028, 2029, 2030, exactly in this sort of crunch time when there aren't a lot of other options. So I would say it's not an easy thing to do. That's why we felt like we had to start this company, because outside of Google and a handful of others that are kind of painstakingly assembling these deals, it isn't the easy button solution. And, what we want to do is using optimization software and using good commercial efforts from our supply team actually make it easy for data centers, as easy as contracting with a gas
And just
plant.
to clarify what we're talking about here, so what you're doing for data centers is you're saying to them, instead of you having to build everything on site, which can often be the most expensive option, we can put together a portfolio of resources for you that we can guarantee are not going to trigger the need for transmission upgrades, right? Because that's the whole point, is to avoid those additional costs of transmission upgrades, right?
Yeah, or at least that they're already in the interconnection queue sufficiently far along that the upgrades required to interconnect them can be completed before your online date. But yeah.
Right. But that's a portfolio. That's not just any portfolio of resources. They have specific characteristics and requires some presumably digging and research and work.
Yeah, and some optimization software that we've developed and, based on the research at Zero Lab. And, it's the kind of thing that we were doing kind of in a hypothetical way in this white paper, was saying, okay, let's use this mix of on-site compute flexibility, flexible generators that are, on-site or close to the, site that we can use to relieve transmission constraints, and then the broader mix of available resources across the grid region to solve this problem. And, it's worth reminding ourselves that this is basically how a utility does its planning, right? If you think about a vertically integrated utility that has to do generation and transmission planning, maybe has some demand flexibility programs in their portfolio, right? They're not turning to one resource to solve the problem. They're developing a portfolio. So we're basically trying to do that wherever the data center needs to show up, because some utilities will do that, but others aren't capable of it, either because of the structure or the transmission owner doesn't own generation, or because they're a small rural cooperative that has a peak demand of 1.5 gigawatts, and now you're trying to connect 600 megawatts to their grid, right? Or, or other circumstances like that, which we find pretty broadly across the country.
One piece of that portfolio, Astrid, that we have not dug into at all, but that I'm endlessly curious about is the compute flexibility itself. So I feel like the conventional wisdom, as I understand it, among the data center folks is flexibility via on-site power resources is easier and cheaper than trying to flex our actual compute load, that the actual flexing of the compute load itself is going to be relatively marginal. But you included in this paper pretty prominently. So of the compute loads that run in these data centers, what percentage of them can be moved around in time or geography in a way that makes a data center more flexible? Is there a set answer to that question? Does anyone know?
Well, yeah, actually, we know a lot about this. And it varies a great deal by provider who's administering the cloud, and it varies a lot by resource type. So part of the reason why we included it in this paper was firstly to, take a kind of forward stance on what's possible. There are some cloud providers today that have the ability to move load around in space and time. Google's capability to do this is probably the most advanced in the industry.
Right. Google's been beavering away on this more than anybody else for longer than anybody else.
It's interesting, just as an aside on this, the reason they started doing that was actually to help optimize their emissions impacts.
Oh, that's actually...
Is that not correct?
No, this work long predates that. The reason that Google does this is for reliability. It's basically their cloud model was built, kind of from the earliest days to be able to move load flexibly between data centers so that in the event of a network failure or a data center failure or a software failure, you'd be able to pretty much instantaneously move load to another location. They have since used that for emissions optimization, but not really in a large scale way. But it's a core part of Google's operating profile.
And can you give us a sense of the scale?
I could drain a data center in under a second. When I was operating large-scale services there, it's nearly instantaneous. And there's a few different ways. Under a second's probably not true. A couple seconds. Their ability to move load partially between data centers or even completely take a data center out of circulation is very, very advanced.
Just to give people a sense of scale, do you think that's going to be a contribution to flexibility that is commensurate with on-site power resources? Less, more-ish?
It could be, but only some cloud providers have that capability. So, for example, Meta has some ability to do this. Microsoft and Amazon both struggle to do this not from a technical capability perspective, but because a lot of their data center usage is from cloud customers. And in those cases, they've often made commitments to provide a certain actual set of resources.
It's a contractual constraint.
It's not a technical problem. It's a contractual problem. Yep. It's saying, like, you got these chunk of servers in this particular data center. You will always have that chunk of servers. Those are yours.
This might be a little bit of a side quest here, but is there anything equivalent to a flexible interconnection?
Yeah.
In terms of cloud providers? In other words, like, you can have this amount of cloud.
Oh, totally.
90% of the time, it's the same sort of.
Yeah. So all of the cloud providers do provide that capability, but because a lot of cloud loads are kind of a lift and shift from the older corporate on-site data centers, where it's like, I had a server in my office and now I have a server in the cloud. Firstly, there's often a lot of difficulty in moving those types of loads around. Like, you have to build differently for a flexible cloud. The other thing is an accounting problem. And we've actually run into this and needed to tackle it for our work with utilities, because in some cases, you basically need to be able to name and then depreciate an asset to fit into the accounting construct of the customer. And then you really need to actually be tied to like a particular location. So there's like nested kind of business problems in there.
I mean, if you've got all these hyperscalers, all these data center people that are panicked to get on the grid and they've got bags full of money, surely they are all working on this, right? Like, pushing compute flexibility as far as they can.
Absolutely. And like, again, the current ability to do this varies between provider. Typically, hyperscalers who actually operate a very large fleet have more ability to do this just because they have more locations to put things. The other that's worth a shout out is there are companies that are offering that capability of being able to curtail in place in a single data center as a commercial option. So Emerald AI, that I was an advisor for and Jesse currently is, they do this as a commercial service.
Compute flexibility specifically.
Yep.
Yeah, they basically provide the sort of operating system and integration with the data center's, job workload management system, so that when they get that signal from the utility to curtail consumption or to respond to one of these flexible interconnection curtailment events, they can then dispatch the compute loads in kind of order of their priority. And so just like the data center looks like a non-firm, a portion of it's firm and a portion of it's non-firm, or interruptible for the utility, it's the same thing going on inside the data center. You have certain jobs that must be served. You have certain jobs that are in different tiers, right, of reliability expectations. And, and if you're in a lower reliability tier, you pay less for that service. And there are many jobs in which I don't need to be 99.99999% reliable. So I'm happy to pay less and be curtailed, 6 hours of the year, right? Or shifted to a different site if that's available.
Yeah.
And so because there's a broad range of players in the data center space besides the hyperscalers, the big names that we're all familiar with, there's all of these other players that build data center shells and then lease out the space inside them to put racks. There are people who lease the GPUs on those racks. There are people who build the entire data center and, basically offer cloud as a service. There's just a huge range of players here, and it's growing, their capacity is all growing.
Yeah.
Having the ability to have kind of a standardized way to do that across all of these data centers is what Emerald's trying to supply to the market. And there are other people trying to solve this problem from different angles as well.
Yeah. So the other thing to think about when we think about the ability to curtail power usage within the data center is that most data centers, they also operate at a kind of low capacity factor relative to their nameplate requirement. So, the grid's maybe 40% utilized on average. The data center is probably 40% utilized on average for the majority of sites.
They're not running at their full rated capacity all the time, even though that's what it shows up in the planning models.
Yes.
In practice, they're not actually doing that.
Depending on the type of data center, but in general, that's true. So for training data centers and also crypto mining facilities, they are peaking to their full power capacity for a period of time and then potentially turning that off for a period of time. So if they're training specifically, they'll use 100% of their nameplate capacity. And for crypto in general, they will also use all of the resources in that data center. But that's not by far all of the data centers that are out there. Most of the data centers that are, serving anything from inference loads to cloud loads, which is the majority of sites that are out there and the majority of sites that are in queue, they have a much more organic variability of the load that they're serving. And they use less of the resources of the facility on average during their serving period of time. But unlike the training facilities, they don't just turn off sometimes. So in both cases, the average utilization is kind of lower than nameplate, but it does matter what kind of data center it is.
It's also worth pointing out that these all have big cooling systems that are a part of that load. So if you have, say, 800 megawatts of compute load, you might have 150 to 250 megawatts of cooling center load, cooling system load at peak, depending on how efficient the system is. And that cooling use, just like your air conditioning at home, varies with the weather as well. And so that also contributes to some of the, kind of extra headroom that you might have when it's not the peak, hottest, most humid day of the year when your chillers are running at their least efficient set point. And so that's also another potential source of flexibility, is kind of making use of that extra headroom when the cooling loads are not at peak, but also changing the cooling load. So I'm working on a project that the former National Renewable Energy Laboratory, now the National Lab of the Rockies, is leading on using ground source geothermal heat exchange, like we have at the Princeton campus here, to shift around the cooling loads and to make them much more efficient when it's hot out, so that you basically can drop your peak cooling load and make extra headroom for compute.
Interesting.
So there's a lot of interesting ideas. Like you said, there's trillions of dollars being spent here. They're all running into the same problem of, how do I actually get what I need from the grid? So that's driving a lot of creativity about different ways to squeeze more out of it.
This brings me to perhaps my most beloved question, which you two are probably like the best two people in the world to ask about this, even though I'm probably going to do several pods on this general subject in coming months, which is, so everybody needs grid capacity. Jesse, you're involved in a company now that is going out and basically gathering grid capacity to sell it to data centers. As you both know, one of the things that I would very much like to see happen is for the spare grid capacity in households and buildings and businesses to be rounded up and to count for capacity that data centers can buy. Because then you can get some of that trillions of dollars diverted into the DER, distributed energy, VPP market, which desperately needs money. I would like some structured way for distributed capacity to count as capacity for data centers so that we can bring some of their resources to bear in developing those distributed resources. This is something I go on and on and on about. Everybody's heard me talk about it a million times. Jesse, you are now doing this. You're rounding up capacity. You're selling it to data centers. Do you have the ability? Is it easy? Is it something you can do to round up distributed capacity? And then on the other side of it, do the data center people and do the utilities you're working with, are they comfortable with distributed capacity counting as capacity?
So we definitely look at distributed resources and demand response, or you can call them virtual power plants if you want, as a potential part of our portfolios at Firma Power. We don't go and round those resources up ourselves, but there are a growing number of players in the market who are doing exactly that.
Aggregators, basically.
There's Voltus, there's Base Power, which does this with distributed batteries. There are a bunch of others as well. And so we would basically go to them and say, how many megawatts can you give us and what date? One of the nice things about them is that they can be done in pretty small increments. So you can kind of refine as you go. And as the load of these data centers ramps up, that's another thing to point out to listeners. Like, you don't turn on a gigawatt data center overnight. You turn it on in stages over the course of probably 2 or 3 years. And so their demands are ramping up over that period as well. And, so there's some value to being able to kind of fine tune and incrementally add capacity.
But you trust that capacity is real. And then when you sell it to data centers and utilities, they trust that it's real.
So I trust it if contractually they say it's real and there's liquidated damages if they don't provide it, right? And I think that's the way everybody should be, entering business arrangements. So I would say on the utility side, again, this is where it's important to differentiate between like the big C capacity and little c. So if you're talking about PJM's capacity market or MISO's capacity secondary market, they recognize demand response as a resource. And so you can participate in those markets. And if we can buy 50 megawatts of accredited capacity from demand response, like we can get that accredited and use it in our portfolio and supply a data center. Where it's a little bit trickier is on the transmission owner side, where the load interconnection happens, where they are under no obligation to accept that as a legitimate solution to their transmission constraints. And traditionally have not thought of those as, in most places, they don't think of those as alternatives.
That's like half the promise. That's like half the
Yes.
That's like half the whole promise of these resources.
Exactly.
Is to
And
avoid
so ideally you'd be getting both value streams, right? You can use them both to solve transmission constraints and to solve, accredited capacity challenges. Right now, I'd say we're pretty confident we can do the accredited capacity piece, but there's still more work to be done to convince utilities that they can count on these operationally to resolve local transmission constraints. And again, there's a wide range across the industry of some utilities happily embracing this and others that are saying, if it's not a gas plant, I don't trust it.
And this is also part of where we come in as well.
Yeah, this is your whole thing.
Totally.
Astrid, so what's your, take the temperature of how much utilities trust distributed capacity resources to do the kind of work we're talking about here?
So I think the distinction that Jesse drew between using distributed capacity for capacity versus for managing transmission constraints is really important.
Right.
I think there's increasing acceptance of distributed resources as a capacity asset and good track records within the industry of folks kind of packaging and providing that service, whether that's the utility itself or third-party aggregators. And I do think that there's a really good opportunity, even in that, to get a lot more money put into the VPP space. But when we look at the bigger picture here, this is it's a different take on the bigger orchestration problem. The goal of employing all of those little resources was to be able to aggregate up small scale demand changes to be able to increase the capacity of the grid and accommodate a lot more demand. When we first started talking about this, we talked about the source of that demand being electrification. So the demand in that model is a bit more distributed, and the solution is also a bit more distributed.
That's still coming.
So that is firstly, that's still coming. But secondly, the data center itself does present a really interesting kind of larger scale version of that problem, where it can bring some of its own tools to mitigate its impact on the grid in the same way that we, long imagined all of the little household devices impact, mitigating the increase in household level demand. And the data center can also choose to just pay for capacity resources or, other services from local distributed resources. And that provides, as you mentioned, a much needed potential additional revenue stream that makes it financially viable to leverage those. And so, that's kind of the way that I still think about this as an orchestration problem, because ultimately what we need to do is understand what's happening on the grid and then be able to dispatch resources, demand, and supply in a way that makes the most out of the supply that we have and out of the wires that we have and will build. And so, long way of connecting this back to, our role and what we offer in this space is that understanding of the grid that can translate into signals to folks participating in it, whether that's distributed resources at the household level or to the data center itself, to say, here's how much grid you have. Here's how much you can safely use.
Right.
Turn it down next Tuesday.
Seems so simple, but
it's real hard.
We've been lacking that basic information to do this.
It's difficult, but not because of the technology requirement.
Yep.
It's difficult because the system has to change.
So, Dave, I know you love VPPs, and I love them as a solution to these problems as well. I want to second everything Astrid said, and 100% endorsement. This is a critical piece of the toolkit that's being neglected right now. I just want to make sure everybody who's a VPP stan out there is also clear. If you're relieving transmission constraints, 1% of the hours or less of the year, and your vision is that then we make better use of the existing grid, which is great to use the transmission lines, but also the generators. It's important to remember which generators are sitting there underutilized, ready to ramp up if you can make better use of them. It's very inefficient and dirty coal and gas plants that are not currently being dispatched because they're less efficient and more costly than the generators that are being dispatched. And this is why we have to do both things. We have to pair the flexible interconnection and distributed VPPs that solve local targeted, transmission constraints, et cetera, and the very needle peaky kind of, generation adequacy events that we might have to deal with. They can contribute to that too, with the, bring your own new clean energy piece of the puzzle, because the other 99% of the hours of the year, you got to consume a bunch of megawatt hours. And if you're not directly contracting for new clean energy that can come onto the grid and meet your demand when you're consuming it in a place that's deliverable to where you are, the grid is going to ramp up idle resources to meet your demand. And that's going to be, inefficient gas and coal plants that are sitting on the
So
sidelines.
if I can summarize, unless we explicitly design it otherwise, these new data centers are going to get served with gas and coal plants that are currently
Yeah, and not exclusively gas and coal, but the majority is gas and coal. And we saw that in our study when we looked at, what happens if you don't require new resources to be brought online.
right. And we should say, I can't believe we haven't said this yet, Jesse and Astrid. I mean, this is in some sense the whole point of the thing, but part of the advantage of the model you're describing is that the data centers are paying for the new capacity that they need when they come online, which means
that
ratepayers are not paying.
Yes,
right?
exactly.
I mean, that's maybe that's obvious, but like that is
no, that's very important to say, and a key part of the solution. Putting climate aside, the principal concern most people have right now about data centers is, are these going to jack up everybody's utility bills? And the answer to that is exactly these two pieces of the puzzle. Avoid a bunch of those unnecessary costs and delays through flexible interconnection, and make sure that data centers are paying bilaterally through a large load tariff or directly, through a retailer arrangement for all of the new energy and capacity that they need. And ideally, that should be clean energy if we care about the, emissions and air pollution's impacts.
Flexible interconnection plus bring your own capacity. So we should at least address the subject of, Astrid, maybe you can talk about this. What needs to happen to make this happen? It seems to me, as I think about this model, there's a lot of parties involved in this that are going to have to change the way they do things to make this work. I mean, I guess the first and most obvious thing is utilities need to more explicitly offer flexible interconnection. What other regulatory or legal changes or reforms do we need to make this model the default?
So this does vary a lot by location. As we mentioned earlier, there are rules in Texas that support this reasonably well today. There's also new rules and proposed ones in SPP, which are called Hills, Chills, and Spills, if you want to Google it, around conditional high impact load additions. There's also a lot of very active conversations in PJM around updating the interconnection model to potentially allow for that idea of like firm versus conditional loads. Some version of that is required to make this model work, but it's not necessarily a huge change from the way that things work today. And so I think that's pretty doable. The other piece of this is that typically the interconnection agreement for transmission capacity happens somewhat separately. It's usually between the data center and the grid operator, the local utility, to make an agreement that accounts for deliverability of power and the actual ability to like plug into the grid. And there you do need the utility to be willing to have a conversation about potentially like offering contingent capacity or a flexible interconnection model. And you also need the data center to be excited about engaging in that conversation. So when we do this now, we often go in with the data center operator who's interested in doing this work to go talk to the utility that they're talking to and say, like, look, this is real. Because one of the things that we ran into when we started looking in this space and looking at providing flexible interconnection for data centers was if you go to the data center, they'd be like, we're interested in that, but will any utility really do it? And then you go to the utilities and the utilities are like, we're interested in that, but would any data center really do it?
Right.
And so that's actually a big part of the reason why we released the study that we did, was to help move that conversation forward, because it was just like two shy people at a dance. Like they just wouldn't talk to each other.
Yes. This is my impression, is that the model is pretty sensible. It seems to kind of address everybody's concerns. Seems like a win-win. So I'm just wondering, like, is the major barrier here just introducing these two shy kids who are standing on the side of the dance floor, or is there anyone against this? Are there opponents?
The opponent is really the status quo.
Yeah, always the main opponent of everything.
It requires making a different sort of interconnection agreement, and most utilities aren't very well equipped to do that kind of analysis today, because you have to, instead of looking at a point in time and a couple of contingencies for an interconnection analysis, you might need to look at, thousands or tens of thousands of scenarios. And so that's where, like, this is actually a little bit a data and software problem.
And that's what Camus does, right? I mean, that's
right.
What you're answering.
And so there's a bit of an industry tool evolution that's required to make this possible. But it's always the process change that's hard, right? Like you need to actually sit down and work with the planning team at the utility and understand like what are their real considerations, how would this fit into their current process. And that's a lot of what we've been doing as we've been working on like making this real.
Well, if there's anything that can overcome the inertia of the status quo, it is giant corporations with huge bags of money. So this actually seems to be happening. It does seem to be shaking loose this incredibly sclerotic industry and sector. It's super interesting to follow. So I guess one question, Astrid, maybe just quickly, is like I think a lot of people who read about data centers, like there are already data centers who are building on-site power. I mean, we were just talking about them. They're building on-site gas. So how's that different from this model? You're just requiring, I mean, I know the flexible interconnection might be different, but in terms of bringing your own capacity, I mean, there are already a bunch of data centers that are not quite completely offline or completely online, right? That have some of their own capacity. So how's this different?
The real difference is that we're talking about incorporating basically as much of the grid mix as possible into the power footprint for the site.
Right. So your on-site resources are just for contingencies, just for outside events.
I think there's sort of two flavors of this. I mean, one is, yes, all data centers have backup generation for contingencies. Usually those are diesel gen sets that are only allowed to run a limited number of hours of the year, or they void their air pollution permits, et cetera. So those are really just for backup. And they also have uninterruptible power supplies, which are short, very, very short duration batteries that can handle little blips in, grid service and things like that and keep running through. The kind of gas rush that we're seeing is often either entirely off grid, or it's in addition to the grid connection. So you might get a 200 megawatt firm grid connection, and then you have 300 megawatts of gas on site separately. Like there's this large project in Pennsylvania that's at the site of an old, I think, 2 gigawatt coal plant, and they want to have 4.5 gigawatts or something like that of total capacity of combined cycles on site. And so, most of those are going to be running all the time because you can't get service from the grid. What we're talking about is if you got a gigawatt scale data center, you have a gigawatt size substation and grid connection. It's just that a third of that might be curtailed at some part of the year. And so I think that's the key difference is like, we need to move between this binary 100% firm or entirely not firm, not supplied at all by the grid kind of world. And remember that those transmission constraints are very, very rare over the course of the year. And they can be managed operationally if the utility is basically willing to do it and has the capabilities to do that.
Got it. Okay. So flexible interconnection and bring your own capacity, and quit building stupid on-site gas plants. And from what I'm hearing, like the pieces of this model are basically in place. The actors have all the motivations they need. Like it's more or less just like a process of hashing it out at this point, just like getting people on board and signed up. But it sounds like this is like there's a lot of open runway here to make this work. I'm curious, like if there's been any reaction. I mean, I know this thing just came out, but if there's been any reaction from the industry. It seems like they would welcome this.
This can be done. Like we have the tools that we need today. It is more complicated than just going fully off grid you have to get multiple parties to agree to it and maybe put together a coalition of the willing kind of perspective. But I think that's where, efforts like what Jesse's company is doing can be really helpful here. And I also hope that that's...
Make it a little easier, just a little more turnkey for everybody.
Yeah, likewise, I think that, stepping into that data and tooling gap with our data center interconnection product also hopefully makes this a little bit easier. And we definitely have seen, I think, a lot of increasingly serious interest from data centers in pursuing this path. I think what will really make this happen at scale is proving beyond a shadow of a doubt that it's definitely going to be quicker.
Yep.
Yeah.
Because once that is clear, there will be no debate about which direction to move.
Yes. Quick is the trump card.
Yeah, because the value of getting online a month earlier is so much higher than all of these things we're talking about.
Yeah, I mean...
So it'll be a competitive necessity.
Our number for the opportunity cost or corresponding value of getting a data center online a year earlier is about $7 billion for a gigawatt of capacity per year.
That buys you a lot of capacity.
It buys a lot of everything.
You could buy a really big VPP for $7 billion.
Yeah, when I mentioned that modeling out what it costs to put in batteries instead of a gas plant was just a couple of extra $1 billion, and that's not super important. Like it's in the context of that opportunity cost number.
Right. If it shaves a year
It pays
off,
back in under a year.
pays for itself 100 times over. That's wild. All right. So faster, cleaner, and a more stable grid. So an excellent model for data centers. Lots of companies and entrepreneurs springing up to make various parts of this easier. Really cool and interesting area to watch. So thank you, too, for coming on and walking through it with us.
Our pleasure. Thanks.
Yeah, thank you.
Thank you for listening to Volts. It takes a village to make this podcast work. Shout out especially to my super producer, Kyle McDonald, who makes me and my guests sound smart every week. And it is all supported entirely by listeners like you. So if you value conversations like this, please consider joining our community of paid subscribers at volts.wtf, or leaving a nice review, or telling a friend about Volts, or all three. Thanks so much, and I'll see you next time.